Hello everyone, my name is Miguel. I'm a second-year PhD student at the ICRA laboratory of Strasbourg in France, and today I would like to present you the work we did on the optimal design of a new kind of robotic system called the AMES, or Area Manipulator with Elastic Suspension. Let us begin. Cable-driven parallel robots, or CDPRs for short, and area manipulators are cost-effective robots that allow to have a large workspace. Because of their relative low cost and easy scalability, they have been widely used in research. Nevertheless, both robots have some inherent limitations. Area manipulators have little autonomy, and the control of CTPRs can be challenging. To address these limitations, our team previously designed the concept of AMES. The idea is to have the simplest possible cable robot using only one passive elastic cable that compensates for the weight of the vehicle, thus increasing the system autonomy. Unfortunately, our first prototype had some design limitations that augmented its energy consumption and limited its workspace. Hence, we decided to explore the optimal design of an AMES with the following objectives. We want to have an omnidirectional area manipulator in order to effectively reject perturbations and do some manipulation tasks. We want to use unidirectional thrusters to simplify the mechanical design. And finally, we want to maximize the robot workspace. The workspace is an interesting criteria because it takes into account the particular aspects of our system, which are the unidirectional thrusters and the spring. The optimal design of omnidirectional aerial vehicles using unidirectional thrusters has been studied in the literature by Tugnon and Franck. A design is considered optimal if the condition number of the wrench matrix is minimized, which can be seen as equally sharing the load among the propellers. However, two optimal designs can have different reachable workspace. This is illustrated in the table where two optimal designs with the same condition number have different workspace volumes. We could not fully rely on minimizing the condition number of the wrench matrix to design our system, so we modified the optimization algorithm, and here are the main steps. We start by generating a random design, then using the results from the Omniplus theory, we locally converge to an optimal Omniplus design, and finally we use the previous results to compute the reachable workspace. The whole process is repeated n times, and at the end the algorithm returns the design with the largest workspace. Using the optimization results, we build a prototype that you can see on the left image. It weighs almost 3 kilograms and uses an NVIDIA Jetson Xavier as an embedded computer. It uses 2 C6 LiPo batteries, and it can handle up to 2 embedded cameras. Finally, it has a small pneumatic gripper for pick-and-place applications. In this video, you can see a trajectory tracking where the robot uses all its degrees of freedom. All in all, in this work, we presented an algorithm that allows to maximize the workspace of an aerial manipulator with elastic suspension and using unidirectional thrusters. Using the results from the optimization, we manufacture and control a prototype. To give you an idea of the improvement, in the right image you can see the workspace of the previous prototype, and now you can see the workspace of the current prototype. Thank you for your attention. If you have any questions, feel free to ask them.